Hi! Today's video is a slight digression from our standard course on topological cyclic homology. In this digression I will define and compute Hochschild homology of schemes for you. So in order to follow this video I'll assume that you know what a scheme is, but this video is not necessary for the rest of the course. So I just want to explain it to you because this is really where these invariants like Hochschild homology and periodic homology and later the topological variance gets very interesting. But for following the basics of the course, this is not strictly necessary. Hi, I'm Thomas Nikolaus from Mathematics Münster. So throughout this lecture we want X to be a scheme over some ground ring K. And K is just going to be any commutative ground ring, not necessarily a field. And again, let me highlight that I'm going to assume that the viewer of this video is familiar with the language of schemes. So I'm freely going to use that. And now the goal of today is to talk about what the definition of Hochschild homology of that scheme X over K is. And by the way, one could also let the base be non-affine, but let's stick to the case where the base itself is affine for simplicity. And basically there are two ways how one could define that. And we could just extend from the affine case. Affine case. And that's what we're going to do today. We're going to adopt approach 1, but so I'm going to explain what I mean by that when I give the official definition of Hochschild homology. But I just want to mention that there's a different approach to that. And the idea in the different approach would be to generalize the functor Hochschild homology blank relative K to something like dg categories over K. Or maybe stable K-linear infinity categories. And then one would define, if one observed that this can be done, you basically write down the same definition that we have done for DG algebras, you just write down for DG categories. So DG category is basically a multi-object version of a DG algebra. And then one would define Hochschild homology of a scheme X over K to be just Hochschild homology of the DG category of the perfect derived category of X. And this approach, then one has to prove that even in the case that X was just a ring, this doesn't change the definition. That's a certain Morita invariance condition you'd have to check. And this you can actually think of somehow, this is in some sense a non-commutative approach. Because these DG categories are, what people sometimes call non-commutative schemes, or maybe specific DG categories you could call non-commutative schemes. This is kind of, I guess, goes back to a program of many people, but Kontsevich has done a lot of work on that with collaborators. And that is the second approach. In some sense, maybe the second approach is, for a lot of things, the second approach is actually better. Because then you see that Hochschild homology really is not an invariant of rings or DG algebras, but it's an invariant of DG categories, or maybe stable infinity categories. But for simplicity, and also because I think it's actually in this course, we're mostly going to talk about rings, I think the first approach is better suited to what we will do. So let me give you the official definition now. And that's the following. For a scheme without any further conditions on the scheme, we define Hochschild homology X relative to K just as the limit U in X, U open affine, Hochschild homology of OU relative k. And that is supposed to be an object in the derived category of k. Or in fact, actually, yeah, let's say it's an object in the derived category of k, and the limit is over the functor, I guess, which is Hochschild homology O blank, which we consider as a functor from the category of affine opens in X. Right? You just take open subsets of X, which are actually affine, and it's a contravariant functor on that, and it goes to the derived category of K. Right? This sends to an affine open O. It will just send Hochschild homology of OU relative K, the structure sheaves evaluated on the affine open. And this definition raises an immediate question, namely, what if X is itself affine? Then we have two definitions. We have Hochschild homology of spec K, right? Hochschild homology of spec, R. So if R is just the K algebra, then we can compute this, commutative K algebra. Then this is now defined as the limit over all U in spec R, affine open, let me just maybe leave that implicit, of Hochschild homology OU. But the point is, in this case, this category of course has a terminal object, right, namely spec R itself. And because it's a contravariant functor, this will be an initial object in the opposite category. And as we've seen before, the limit over a category which has an initial object is just evaluation on that object. So what is this? This is just Hochschild homology of O evaluated on spec R relative K. But this is of course just Hochschild homology of R relative K. So in that case, this definition doesn't give anything new in the affine case, but it extends our definition of Hochschild homology from the affine to the non-affine case. And really, if you would like, one could actually go a little further beyond schemes here. One could even define that for stacks or something like that. But let me go stay in the realm of schemes for today. Okay, good. That is the definition of Hochschild homology in the non-affine case. The main question is now, well, this definition looks very universal. I mean, it's in fact actually a right-Kahn extension. And how does one ever compute this? How does one get your hands on that? And as an example, let's look at projective space. Projective space P1 over K is just a scheme. It's a scheme over K, and of course here we have to work a little bit. I mean, now I guess this scheme has a lot of open sets, but the way we want to think about it, I mean, usually the way you study it, or maybe you even define it, is that it has an open cover consisting of two copies of A1. A1 over K, which is just spec Kx. And maybe you have another copy, maybe this is A1 plus, and there's another copy of A1K minus maybe. This is plus, minus, this is maybe spec K over Y. And the intersection, I mean, this sits inside of, I mean, this A1 minus, I guess, or let me say the intersection of A1 plus K and A1 minus K, both of which are considered as subsets of P1, this is just going to be GM. This is just going to be GM, which is spec of K adjoint X plus minus. And Kx maps to Kx plus minus by sending X to X, and Ky maps to Kx plus minus by sending Y to X to the minus 1. And I mean, these are the open sets which we somehow understand. And now the question is, how can we somehow, I mean, these are affine, so for those we know what Hochschild homology is. And now the question is, can we reassemble the computation of Hochschild homology from these two open sets in P1? So And this is a question of descent. Descent, or maybe if there's some sort of Meyer-Vietoris principle, Vietoris sequence. Right, if we somehow, we know how to compute Hochschild homology of these three patches, can we compute Hochschild homology of P1? And of course, I guess by now you already guessed that the answer will be yes. And that is the following theorem. That is Zariski descent, maybe. It says for any pair UV of open subsets x of x such that, well, I guess x is the union of u and v, so subschemes. The square, and of course I give this like the full subscheme structure. The square Hochschild homology x, and then I can restrict to Hochschild homology u and Hochschild homology v. And maybe I should always write relative k. And Hochschild homology u intersected v is a pullback in dk. And maybe here I'm using something, so I guess here I have the inclusion. So this is pullback along the inclusion, and here I have pullback along the inclusion. And I mean the same here, I guess. So I should maybe note that I haven't said this before, but it's not hard to see that this defines actually a contravariant functor on the category of schemes over K. And when I say this is not hard to see, this is not hard to see by believing that the limit behaves sufficiently functorial in the indexing category, and that's something we wanted to use as a black box. So I don't want to really go through how you make this infinity categorical limit. So this is an infinity categorical limit, fully functorial, but this can be done, and so this is obviously a contravariant functor on the category of schemes over K. And then this is the functoriality. This is just the inclusion u intersected v into u. This is the inclusion u intersected into v. And then you have the inclusions from u and v into x. And this is the square, right? You get a commutative square. And the statement is that this is a pullback square. And more generally, or actually in fact equivalently, one could say that Hochschild homology as a functor satisfies Zariski descent. And in fact, actually it satisfies more, and we will need that in this course, but not talk about it now. So let me just say we will see at some point that Hochschild homology blank relative k as a functor from, say, schemes over k satisfies even more. It satisfies even étale descent, or in fact even more generally, even flat descent. Flat, and maybe for the experts, FPQC descent. Right. But I want to stick to this more basic setup of Zariski descent, because this will be what we will need in practice for the moment. And once you have that theorem, you actually get as an immediate corollary in the situation of this theorem we get a long exact sequence. A Meyer-Vietoris style sequence. How does this look like? I guess we want to compute Hochschild homology in degree n of x. And then we have the map to Hochschild homology in degree n of u plus Hochschild homology in degree n of v. And then we have Hochschild homology in degree n of u intersected v. And I guess maybe I should say this is I upper star comma j upper star. And then I guess this is the difference of the two maps from x into u and x into v. So you have to put a sign onto the second component, say, just as in the usual Meyer-Vittori sequence. And then you go to Hochschild homology in degree n-1 of x. And here, I guess, connecting homomorphism comes from Hochschild homology in degree n+1 of u intersected v. Okay, so that is the Meyer-Vittori sequence you get for every pullback in a stable infinity category, actually in the derived category of k. And how can we leverage the sequence now in order to compute Hochschild homology of x? And for this, actually, we first, of course, I guess we haven't really talked about this. So what we know is that this here, actually, we can compute Hochschild homology of kx and we compute Hochschild homology of ky. But what is Hochschild homology of k adjoint x plus minus? And there's this little lemma which says the following, then that Hochschild homology for any commutative ring, say commutative ring, this is a little bit more restrictive than necessary, and x an element in R, we have that we want to compute Hochschild homology of R x to the -1 relative k. And the claim is that this is actually given by taking Hochschild homology R relative k. And then you invert x. So in other words, you base change this along R to R adjoint x to the -1. So one thing to note is that we have seen before that this is in fact an R module. So this was in fact by the shuffle map. And so you can make this base change. And maybe you want to write the right hand side simply as Hochschild homology R relative k adjoint x to the -1. Right. So in fact, computing Hochschild homology of a localization, by this here I just mean the ring obtained by adjoining an inverse to x. And I want to leave this lemma as an exercise for you to work out. This is basically an exercise in the definition of Hochschild homology. And then one knows how to compute Hochschild homology of GM. So let's continue our P1 example. And by the way, I want to prove the theorem, or at least give you an indication of proof why we have these pullback squares. But let me first run through this example. And this example is again P1. So we have that Hochschild homology of P1 is now the pullback Hochschild homology of this A1 plus, which is spec kx relative k. Or maybe I don't write the spec here. Just to. And then I have Hochschild homology of the A1 minus, which is also ky relative k. And then I had the map here to Hochschild homology of kx plus minus relative k. And that is a pullback in the derived infinity category dk. And that, I mean, what is this map? This is the map which sends x to x, and this is the map which sends y to x to the -1. Right, and what do we know about the Hochschild homology groups here now? So in degree 0, this is given by ky, and in degree 1, it's given by ky times dy. So it's a one-dimensional module over that, and then it vanishes above degree 1. This also vanishes above degree 1, and by this lemma, we get that this is in degree 0 given by kx plus minus, and in degree 1 also by kx plus minus. But maybe want to think of the generator of degree 1 as dx. So what does the Meyer-Vittori sequence looks like? So I guess, so we have that, let's see. So we have Hochschild homology. Let me see how this is arranged optimally. So Hochschild homology in degree -1 P1 relative k. This maps to 0. So this is sitting in positive degrees, those two guys. So this is the minus first line, and in fact, actually, I guess immediately we see that Hochschild homology in degrees less or equal minus 2 here is 0, right? Because I guess all these terms vanish in negative degrees, so we will continue with 0. Let me not draw that. So this would continue down here. But then what is the next step we get? Here we get a map from, now we have the Hochschild homology of the intersection. So we have Hochschild homology in degree 0 of this guy. So this is given by kx plus minus. Okay, let me draw the arrow like this. And then here we have Hochschild homology kx plus ky. And what does this map do? This map sends a polynomial f comma g just to f of x plus g of x to the minus 1, right? So that's this map. And then here we have Hochschild homology in degree 0 of P1. And then here we have the next term, which is Hochschild homology in degree 1 of this guy, right? So this is given by kx plus minus as well. Maybe I write it like this. This is degree 1. And then here we have kx dx plus ky dy. And here we have Hochschild homology in degree 1 of P1. And then we get higher terms, so that's all 0. So the only degrees where Hochschild homology of P1 could be non-zero is 1, 0, and minus 1, right? Okay, so now let's think about this map here. What do we know about this map? Well, this map is obviously surjective, right? So because obviously, I guess I could just write any polynomial, any Laurent series, Laurent polynomial here as its positive part and its negative part, and both of these come from here, right? So in fact, so we conclude that actually from this long exact sequence that Hochschild homology in degree minus 1 of P1 is 0. That's the first immediate conclusion. Then we have the next conclusion is that what happens here, what's the kernel of this map? So I guess it's obviously those two can't give the same element unless the polynomial was constant, right? If I have some constant polynomial, say alpha here, and I put minus alpha here, then the two would go to the same element, and that's clearly the kernel. So what I see is that in this degree, the kernel here is the k. And now let's think about what this map actually does. So this map sends f dx, comma g dy. Where does it send it to? Well, it sends it to the element f dx. And then where does g dy go? This is, maybe I should write f of x dx. And then I have the element g. I would just insert x to the minus 1. But then dy goes to, I guess, y goes to x to the minus 1. So dy goes to the derivative. So it goes to 1 over, I guess, minus 1 over x squared. And then dx. Right, so the element f comma g, if I ignore the basis elements, goes to fx, gx to the minus 1 times minus 1 over x squared. Right, and so I guess now I have how surjective is this map? And I guess with roughly the same argument as here, you see this hits almost everything. The only thing you can't hit is because here we have a minus 1 over x squared. The only thing which we cannot hit is actually 1 over x. Right, so this has a one-dimensional co-kernel over k actually. So we see that actually Hochschild homology 0 sits in a short exact sequence with k, Hochschild homology 0 and again a k, which then obviously splits. So we get that Hochschild homology in degree 0 of P1 over k is actually given by k plus k. And what happens in degree 1? Well, I guess in degree 1 we see, what about this map? And here you see this map is clearly injective because these two terms can never give the same. I mean, this only has like non-negative powers of x showing up, and this has powers less or equal less or equal -2, yes. So they can never agree, so actually it's injective, this map, so Hochschild homology in degree 1 of P1 is actually 0. And that is what you get. Hochschild homology of P1 is actually, in fact, concentrated in degree 0, and they're given by 2 copies of K. Okay, so now let me give you a little bit of an indication as to why this Meyer-Vietoris sequence exists, or why this square is a pullback in general for open sets. Proof of the theorem. And so remember we had U and V open subset of X, and what we want to show is that Hochschild homology of X is the pullback of Hochschild homology U and Hochschild homology V over Hochschild homology U intersected V. And here I guess I leave the K implicit. And remember that actually we have that this here was an inverse limit of, I guess now I'm running out of letters. What is a good letter for an open? Maybe say A in X, Hochschild homology A. And now here, basically, a priori, by definition, you would have to take all open subsets of U and all open subsets of V, right? Open affines, I guess. And somehow, I guess the first reduction step one can do, and I will not precisely go through how this reduction step goes, that one can also write this as an inverse limit of the same A in X over Hochschild homology A intersected U. And then this here is also A in X, Hochschild homology A intersected U intersected V. And here we have limit A in X, Hochschild homology A intersected V. And that's basically a cofinality argument. The reason I don't want to go through that is because we haven't talked about cofinality. But that trick lets you, because now we know that the inverse limit commutes with pullbacks. So now we see if we, for every affine open A, we know that this square inside without the limit is a pullback. HHA intersected U, HHA intersected U intersected V, and HHV. Then we conclude that the whole thing is a pullback. So without loss of generality, we can assume that X is in fact affine. But then the point is, even if X is affine, this doesn't mean that open subsets itself are affine, right? So there could be non-affine open subsets. So there's a next step which also is a sort of cofinality argument. And again, I don't want to go through this. One can also assume that U and V are affine. And this is, I guess, to do this, you'd have to think a little bit about, I guess you first prove the theorem in this case, and then you use some sort of Zariski descent style trick in order to get that. And I guess one has to be a little bit careful. Let me not go through this, but you want to sort of have finite open, so you want to use some sort of quasi-compactness. Anyway, so thus, and I also want to assume, and they are standard open. Thus, we reduce to the case where we have Hochschild homology of a ring, and then we have Hochschild homology of R adjoint X to the -1 relative K, and we have Hochschild homology R Y to the -1 relative K, and here I have Hochschild homology R X to the -1 Y to the -1 relative K. and such that, I guess, these two open sets cover spec R. That means that one is element x plus y. Or I mean, let me say it differently. One is of the form alpha x plus beta y for some alpha and beta in R. So x and y are elements in R, which you invert here, and I guess you want to say one is of this form. And again, I mean, this reduction is a little subtle, but let's just take the fact, I mean, if you know a little bit about schemes, you probably know how this reduction is done. And if not, then just note that this is a special case of our main theorem. This is just a special case where we have these two open sets. So that's the intersection of these two sets. And so the question is perfectly valid to just prove this special case. And maybe I should have said I'm also using that Hochschild homology sends disjoint unions to products, of course. I didn't really want to talk about that, but that also goes into the reduction. But anyways, let's not worry about the reduction too much, but let's start looking at this case. In this case, we get from the lemma that Hochschild homology, I mean, Rk is what it is, but then what was Hochschild homology of R adjoint x to the minus 1? This was just given by Hochschild homology R relative k, and then we tensored over R with R adjoint x to the minus 1. And by the way, I guess we want to make the implicit convention that every tensor product is always derived, but in this case it doesn't matter because R at x to the minus 1 is always flat over R. So in that case, I guess the derived and underived tensor products are the same. And here we have Hochschild homology R relative k tensor R with R y to the minus 1. And then we have Hochschild homology R relative k tensor over R R x to the minus 1 y to the minus 1. And so we have to show that this square is actually a pullback. To see that this is a pullback, it suffices to prove that, I guess, this square is just obtained from the square R x to the minus 1 R y to the minus 1 into R x to the minus 1 y to the minus 1 by tensoring over R with Hochschild homology R over k. So it suffices to show that this is a pullback. Because, I mean, pullbacks stay pullbacks after, say, I guess, derived tensoring with something, but that's why I already said that the derived tensor product and the non-derived tensor products agree. And that is, of course, a standard fact. How do we see that? I mean, to see this one, I mean, this is true. It's true because I guess one way to check that this is a pullback by means of, I guess, the 5 lemma in the Meyer-Torres sequence is to say that the co-kernels here agree. And so you have to worry whether x to the minus 1 modulo R, and this is like maybe the cofiber, a derived mod. Let me write it like this. Agrees with R y to the minus 1, I guess x to the minus 1 y to the minus 1 mod ry to the minus 1. But why is this true? I mean, I guess in this case you can just pull the y to the minus 1 out. This is just a filtered colimit. So it suffices to see that on this guy y acts already invertibly. Right? So, and this is because, and why is this true? This is true because I guess I want to say checking that y acts invertibly on this guy is equivalent to saying that the cofiber of y is actually already 0. And this is because on our mod y, x acts invertibly. Right? Because I guess if we quotient by y or take the cofiber by y, we can as well pull the x out. So you have to check that this map r mod y into r mod y x to the minus 1 is an equivalence. But this just is the case if x acts invertibly. But that is again true if we just quotient by x and then it's 0 on r mod y. So in other words, if we take x, r and quotient by x and y, this has to be 0. But this is obviously the case because 1 can be written as ax plus by. Or said differently, if we quotient by y, then x is already a unit by this equation. And of course, again, the quotient is taken in the derived sense. Okay, good. So that finishes this proof. And again, modulo the fact that I haven't done the reduction really carefully. But okay, so that is how we see that Hochschild homology satisfies Zariski descent. And let me again highlight that, in fact, it satisfies flat descent. And what can we say now in terms of HKR theorems? So recall what was our HKR theorem or HKR filtration. So we saw that if R has flat cotangent complex, L R over K by flat, I just mean that the cotangent complex is flat as an R module and concentrated in degree 0. And this is, for example, the case if R is smooth. Right? Then we had that. I guess that was our HKR theorem. We have seen that HHR relative K on homotopy groups is actually given by the Ram complex, right? Omega star R relative K. And the question is now, how does this statement now globalize? So in general, we had a filtration, the HKR filtration, F HKR star HH R on Hochschild homology R relative K by. In general, I mean without any assumption on R. And I mean the statement was that whose associated graded is given by the derived Ram complex. Or I mean whose n's associated graded is given by, and by n's associated graded, I guess I mean I have the n's HKR filtration on Hochschild homology, and then we had the map from the n plus first. This was an ascending filtration. And so the cofiber here, this is given by the n's, the non-abelian derived functor of the Kähler differential, of the n's power of the Kähler differentials, and then shifted up into degree n. So that is this term. And again, I guess as Achim has explained in his video on the HKR theorem, this is just the non-abelian derived a composite of two non-abelian derived functors. It was kind of the non-abelian derived functor of taking the exterior power after applied to the cotangent complex R relative K, and then in the end you shift up everything to n. Right, so that's a general theorem. Even, I mean, without our flatness assumption, we have such a filtration. And that was completely canonical, and this filtration is complete in the sense that the inverse limit over f HKR n plus 1 n HH R relative K is actually 0. I mean, this is a filtration. The zeros filtration piece is just Hochschild homology, and the inverse limit is 0. And this is because we've seen in Achim's talk, and I guess it also follows immediately from this formula, that the n sky is at least n connective. So it has no homology groups below degree n. So it gets higher and higher connective, and it's a general fact that if you have a limit over things which get higher and higher connective in the derived category of K, then this is 0. This has to do with the T completeness of that category. So that's the limit in dk. So that's a sense in which this is a complete filtration. Right. So I guess now we can define a similar filtration. Similar filtration, or the same filtration, or we extend this filtration on a Hochschild homology of a scheme. As, I guess you just define the nth filtered guy, the HKR filtration of x relative k as just the inverse limit. I mean, I guess we take u and x, affine open, of the HKR filtration. The nth piece in the HKR filtration of Hochschild homology OU relative K. So the same way that we extended the definition of Hochschild homology from the commutative case to the from the affine case to schemes, we extend the HKR filtration from the affine case to schemes. And note here, this cannot, I mean, really not be done in the non-commutative setting, because here we're using something about the HKR filtration, which is some commutative thing. Right? So this is one reason why in the beginning I decided to use this limit definition of Hochschild homology. And again, and maybe let me write this as a proposition. This defines a complete filtration on HHX relative K, i.e. The inverse limit over n fn HKR of x relative K. Maybe I should have written somewhere Hochschild homology, but let me stick with the notation as I have it now, is actually 0. And the nth associated graded is given by the, I guess, or let me say it like this. So inverse limits commute with cofibers. So the cofiber was this. So it's given by the inverse limit u in x of L omega u relative k. I mean, this is affine open of the nth guy n here. And this you might want to write as R gamma of x with values in L omega and R relative k, or maybe O relative k, shifted up by n. And this is called this is the derived Hochschild homology. Of x. What do I mean by that? So let's see if x is actually smooth. If x is smooth, then so are the affine opens, And then we see that, in fact, this is just the sheaf omega n. Then the derived de Rham complex just agrees with the ordinary de Rham term. And then this is just the sheaf omega n. And this is just then the sheaf cohomology of X with value in the sheaf omega n. And that's a classical Hochschild cohomology. But this is just a derived version of Hochschild cohomology. And again, I mean, the difference between derived and non-derived only kicks in as you're in non-smooth settings. In the smooth setting, this is just saying that we have a filtration on Hochschild homology and whose associated graded is the Hochschild cohomology. So, and I guess proof of this proposition. Why is this true? I mean, this proposition contains two claims. The first is that this filtration obtained as a limit is complete. But this is in fact obvious because being complete just means an inverse limit is 0. And inverse limits commute with inverse limits. So if you just want to prove that this inverse limit is 0, you just interchange it with the inverse limit defining this and then use the fact that it's 0 here. So the completeness is obvious. And I guess we really use the completeness here. You have to be a little bit careful about the fact that somehow I'm not claiming that these things are still as connective. So the completeness doesn't really, but the fact that limits commute with limits helps us here. And for the second part, again, you're just observing that this is just the limit over the affine opens. And cofibers commute with limits. So this proposition is completely obvious once you state it correctly. So in particular, we get a spectral sequence from Hochschild cohomology, from derived Hochschild cohomology, I guess R gamma n, which is just the nth homology of that chain complex, L omega k, O relative k, sorry, shifted by k. Maybe I should write the k here and the n there. Which converges to Hochschild homology. K plus n, I guess. I mean, just write star of x relative k. For every scheme x. So this is kind of the analog of the Hochschild de Rham spectral sequence. Sorry, no, this is not the analog of the Hochschild de Rham spectral sequence. We will talk about the Hochschild de Rham spectral sequence in a future lecture, but this is just the Hochschild to Hochschild homology spectral sequence. And I guess one can wonder whether the spectral sequence degenerates or whether it's actually true that Hochschild homology is still somehow just the direct sum of these associated graded pieces, which is basically what we've seen in the affine case, in the rational case at least. And I mean, this is maybe an immediate corollary. And this is a corollary, maybe not quite of the HKR filtration, but of what we've done before. One corollary is that if K is contained in Q, Q is contained in K, sorry. Then I guess we've seen before in previous lectures that then Hochschild homology is actually, let me state the statement first. Then Hochschild homology of any scheme x over k is actually canonically the product of the R gammas x with values in L omega n, R relative k, O relative k, shifted up by n. And why is that? This is proof. So I guess earlier in the lecture we have seen that this is true if X is a polynomial ring. And in fact, I guess we've seen it as soon as the HKR theorem was true, we've actually seen that there was a map from Hochschild homology into the de Rham complex or the de Rham terms with zero differential. So another way of saying that is that this was the direct sum. But note, in that case, actually, it doesn't make a difference whether I put direct sum or direct product here, because then the Hochschild groups, I mean, the de Rham complex sits completely in positive degree. And then, I mean, it follows that it's also true for any x, for any affine x, by a non-abelian derived functor derivation. So if x is going to be affine, then I guess we have seen that Hochschild homology R relative k is just the non-abelian derived functor of the Hochschild homology on polynomial rings. And then you just have to observe that the left-hand side is also non-abelian derived. And you might in this case be a little bit worried about the fact that this is that this guy is actually a product and not a sum. But note, I can just replace this product effect by a sum. It doesn't make a difference because I guess, I mean, the nth guy is just going to be n connective. So in every single degree, you only have finitely many contributions. So I could as well just put a sum here. And that shows it in the affine case, and then the general case follows. And I've actually used something here which, so my proof is a little bit fake for the fact that, in fact, I need a natural map to begin with to make the statement. And somehow I have produced the natural map. There was this map that I had written down earlier from the Hochschild homology. That's where I needed Q and K to the de Rham complex with zero differential, right? This map which involved 1 over n factorial in degree n. And that map is actually completely functorial. So as a result, you see that this proof not only produces the equivalent, I mean, this also produces the map, right? You just define it for polynomial rings, and then you start first taking the non-abelian derived functor here, and then you're gonna take the further limit. And that proves this result. And in fact, this proves a little bit more because I carefully, when I talked about the fact that we have this equivalence between Hochschild homology and the de Rham complex with zero differential in characteristic 0, I also talked about the B operator. And so in fact, actually you could say, and I will say that, but not today, that this is actually an equivalence compatible with the B operator. So I guess I could already say that. There is a B operator here, there's coming from the de Rham differential, the non-abelian derived map coming from the de Rham differential, and there's a B operator here. And this map is in fact compatible with the B operator. And so in fact, we'll see that we do get a spectral sequence or sort of a decomposition even in the case of periodic homology. But I will save that for future lectures because the B operator was a little bit fishy, and as in how it interacts with the multiplicative structure. And so the goal is to first make sort of precise what the B operator actually is in infinity categorical terms. And then we'll get back to these statements and make statements about not the Hochschild homology, but the de Rham homology. But not today. I think for today I'll finish here. And thank you very much. Have a good end of the year. I hope see you back and stay tuned for further videos in the future. Thank you.